Okay, so hello everyone. My name is Ramadhan from School of Computer Science, Bina Nusantara University, and today I'll be presenting our paper Oversampling Techniques for Imbalanced Sentiment Classification, a comparative study of SVM and LSTM, which has been submitted at to ICIMTech 2026. Okay, so here's our background. Sentiment analysis is widely used by businesses, researchers, policymakers, and to understand public opinion from social media data. The real world data is messy, like we know, especially in Twitter data. You rarely get an equal number of positive, negative, or neutral tweets. This is called class imbalance, and it makes model favor the majority class while performing poorly on minority classes, especially neutral, which is usually the hardest one to predict. And a common value point in sentiment analysis is misreading neutral as negative or positive, and this directly distorts public opinion metrics, since neutral tweets often present the largest silent portion of real-world conversation. There are two common ways to fix this. The first one, you can change the algorithm, and the second one, you can fix the data through something like me. And we also focus on the second approach, using three popular oversampling techniques, which are smooth, borderline smooth, and random oversampling, or ROS. Okay, so here is our gap. Oversampling techniques have been tested a lot, but mostly sparingly, either one classifier or one data type at a time. What has not been tested much is how they behave when applied to two very different classifiers side by side under the exact same condition. That is our gap. And we also compared SVM, a feature-based model, and LSTM, a sequence-based deep learning model. And our questions were, how much do these techniques actually improve minority class perform improve minority class performance for each model, and which technique works best for each one and why? Okay, and this is our datasets and preprocessing. We used the Twitter entity sentiment analysis datasets from Kaggle, about 59,669 tweets after cleaning, and we split them across negative, positive, and neutral, with neutral with the smallest being the smallest, as like I said before. And as you can see, in this chart, the imbalance is fairly mild. Negative is around 38%. Positive is sorry. Positive is 35%, and neutral in at 31%. We did standard preprocessing, lowercasing, removing URLs, mentions, hashtag, and stop word. So SVM used TF-IDF factorization, while LSTM used tokenization with sequence padding. And importantly, oversampling was applied only to the training data. The test set stay untouched the whole time to keep our evaluation realistic. Okay, and here's our pipeline. Raw data goes through pre-processing, then an 80 per 20 test split. We apply for sampling settings, baseline, smooth, borderline smooth, and ROS to two models, which are SVM and LSTM, that gives us 8 total conditions. And LSTM was trained for 5 epoch using the Adam optimizer, and SVM was trained with a fixed random seed for reproducibility. We also evaluated everything with using accuracy, precision, recall, and macro F1, since that treats all three classes equally, including the minority one. Okay, so let's take a look. For SVM, the difference were really small. All four bars are nearly the same height, within about 0.005 for each other in macro F1. Borderline mode was technically the best at 0.7735, but honestly, SVM with TF-IDF already handles imbalance pretty well on its own. Oversampling didn't add much here. Okay, so here's for the LSTM. LSTM tells a completely different story. This is the most important chart in our entire study. Smoke caused a dramatic collapse, dropping macro F1 all the way to 0.3160, and borderline mode also underperformed at the baseline. But ROS here, shown green, yes, gave us the best result of the entire experiment at 0.7999. But why? Maybe because Smooth creates synthetic samples by interpolating between data points, but LSTM input is sequences of token IDs, and interpolated values don't correspond to any real token. So instead of helping, it just introduces noise to LSTM. And ROS doesn't have this problem because it simply duplicates a real sequences, keeping them fully intact. Okay, so here's the per class F1 for LSTM. To understand the collapse better, we broke it down per class. Look at the smooth row here. Negative, negative is 0.57, and positive is 0.37, but neutral is exactly 0.00. The model completely stopped predicting the neutral class altogether. Compare that to ROS, which is actually achieves the best balance across all three classes: 0.84, 0.77, and 0.80. So this confirms Smooth isn't just slightly worse for LSTM, but it's fundamentally incompatible with it on this dataset. Okay, so here's our discussion and limitation. So the key insight is the right oversampling techniques depends heavily on the model architecture you are using. Smooth is relatively safe for SVM, but it's too risky for LSTM, where it can cause catastrophic collapse. And ROS turned out to be the most robust technique for LSTM in our experiment. And of course, there are limitations. Our dataset has a mild imbalance ratio, around 38% versus 31%, roughly 1.2 to 1.0. Results may not hold for severely imbalanced cases, for example, 9 to 1, 10 to 1, or higher than that, where oversampling effect could behave differently. And our LSTM also didn't use pre-trained embedding like BERT, PERT, or GLOVY, and we only tested 3 oversampling techniques. Future work could explore GRU or transformer-based models and other techniques like Yaasiin or back translation. Okay, so this is our conclusion. To conclude, for SVM, oversampling only gives a marginal effect. The choice of technique is critical. Smooth causes severe collapse, while RS performs best overall. The main takeaway is simple. There's no universal oversampling method. As we put in on the slide, the bottom side, architectures matter more than the technique itself. Okay, so that's all I can say in this presentation. If there's any question or feedback, you can reaching me out via my email. Okay, thank you for watching, everyone. See you next time.